In this video, I'm going to demonstrate Hayes and Chi's approach to adjusting standard errors when the data are consistent with heteroscedasticity. And in this example, all the tests point to yes, the data do not satisfy the homoscedasticity assumption. Therefore, I can't trust the standard errors and I can't trust the p-values associated with any of the statistics. Now, Hayes and Chi have developed a macro that can be used in SPSS that estimates adjusted standard errors, and then you can trust them if you have violated the assumption of homoscedasticity. Now, I do mention here briefly that I believe the Hayes and Chi method does assume relatively normally distributed data. So if your data are insufficiently normally distributed and you violated the homoscedasticity assumption, you'd probably want to use the wild bootstrap in order to estimate the standard errors and the p-values. But if you're not prepared to do that, and you just want to use the Hayes and Chi method, and your data are not non-normally distributed, then you might consider this method. So to apply this method, you need to obtain the syntax file. I gave a link in the chapter to get this syntax file. It's basically a macro, and you need to run it to put it into memory. So run and click all, and now SPSS is prepared to run this macro, but you need another line of syntax. So go into File, New Syntax, and what you need to include there is the following. You need to call it up. HCReg is the name of the macro. This is going to make reference to the macro that you just put into SPSS's memory. And then you've got dv equal, and you need to make sure it's consistent with the dependent variable in your data file. So in this case, it's called earnings. You can see this is the dependent variable called earnings, and the independent variables are called education and IQ. So if I go back to that syntax file, I've got \iv equals education and IQ. So that's all I've got to write. So this is going to be written in every person's syntax, HCReg, that's the name of it, and then everyone should write dv equal, and then you would put the name of your dependent variable, \, everyone would write iv equal, and then the names of your independent variables. In this case, it's education IQ, and then click Run. And SPSS produces the output, and the key portion here is the standard error, and these are corrected. HC is for corrected standard error. You can see that the unstandardized beta weights are exactly the same as when I ran the analysis just on the raw data. These are the same unstandardized slopes I've been showing across many videos now. That's the same thing here, same intercept, same r-squared value, 0.130. But then we've got the standard errors, which are heteroscedastic corrected or adjusted. And we can see that education with the standard error of 865.5699 is still a statistically significant contributor to the model, but IQ is no longer. It's got a p-value of 0.0568 because this standard error has been adjusted. Look how it's 262, but in the non-corrected standard error, it's 208. It's smaller. So the Hayes and Chi method has increased the standard error, and it's increased it in such a way that the p-value is no longer statistically significant. It was 0.017 non-adjusted, and now it's 0.0568 adjusted. So something that's interesting about violating the assumption of homoscedasticity is that you don't know necessarily what direction the adjustment is going to go. You can violate the assumption, and then the corrected or adjusted standard errors are actually adjusted downwardly, and you increase the chances of rejecting the null hypothesis. So it doesn't always go up, it can go down. So this is the Hayes and Chi method of correcting standard errors in the presence of heteroscedasticity.